I'm going to talk about Flamingo, our research effort to accelerate carbon footprints for consumer products. This work is in collaboration with my esteemed colleagues at Amazon, shown here. Carbon footprint of consumer products is essential to understand how we are going to reduce greenhouse gas emissions and reduce the impact of the corresponding climate change. Consumer products account for about 75% of the global emissions. And associating the appropriate emission to each of the things that we use on an everyday basis is an essential step to changing our consumer behavior, the production processes, to finally get to the point where we are carbon neutral. Let's take an example of carbon footprinting with a paper towel. If we just take the energy that gets consumed either through fossil fuels or electricity, we would get the associated carbon dioxide emissions, and that could be one way to do carbon footprinting. Turns out that's not the right approach. We have to take a more systematic view where we look at the entire life cycle of how the raw materials get sourced to how the product gets disposed. This method is called life cycle assessment, and the figure here is showing all the steps associated with doing carbon footprinting for the paper towel example. And as you can see, the product manufacturing is actually a tiny portion of other steps, like how is the raw material, the wood that's used for pulping, sourced? How is this processed? How is it packaged? All the transportation that's associated with shipping these materials around. How is this distributed to the customer if the customer returns those packages? And how is it disposed? Whether you recycle or compost has a significant impact on the final emissions. More generally, life cycle assessment accounts for environmental impacts from each aspect of a product. And it can be generalized to assess the impact of other categories like water use, toxic waste, and so on. This is a scientifically accepted method that has been coded into the Greenhouse Gas Protocol and several international standards. However, getting the direct measurement across the entire supply chain and downstream use and disposal is challenging. Therefore, practitioners rely on existing LCA studies. And these LCA studies are encoded as environmental impact factors and collated into databases by vendors such as EcoInvent, AgriBelize, Gabi, and so on. Some examples of related to our paper example is shown here, such as how much carbon emission is associated with building a pulp factory, bleaching the bleached pulp from the wood that we get, and growing the wood itself. The EIF datasets are passed to LCA practitioners as spreadsheets today, and they do manual Control F based searching to find an appropriate match. It is this portion that we are going to focus on and make it easier for the LCA practitioners. Exact string match has several issues, such as it doesn't capture the semantic meaning behind the words, so it can miss things like abbreviations, synonyms, set relationships, and so on. A well-established solution is using language models trained with neural networks. To our knowledge, we are the first to study neural language models for this problem. And when the basic idea is that the words get encoded into vector representation, the representation itself is based on the neural network trained on web scale data. So it generalizes to most domains. And it can, by matching the vectors using a distance metric such as cosine similarity, you can find the closest match in an EIF dataset. This works quite well. Here is an example of a sea salt. Not only does it capture the exact string matches, but related concepts such as sodium and potassium chloride. And if the user were given this search bar and the ranked list shows up and they select an appropriate EIF, then it's much easier and less effort compared to looking at the same results through over a spreadsheet. However, neural search ranking is designed to search across millions of data points. And EIF datasets are not so large, and many of these things we are looking for may not actually exist. Here is an example of a mushroom which does not exist in our dataset, and the neural ranking shows all the related vegetables that are present, but they cannot be used as a replacement for emissions associated with mushrooms. So they are semantically related, but the carbon emissions might be quite different. To address this problem, we introduce an intermediate layer before we select the final EIF for recommendation to the user. This intermediate layer consists of industry sectors that captures all of the different things that can exist in the world. And if a certain category of EIFs do not exist, then we can tell that there is no corresponding EIF for this product by matching the product to an intermediate industry sector. We use the harmonized system codes as the intermediary layer because it's a well-established system developed and maintained by the World Customs Organization for worldwide import-export taxes. An example is shown here where all the products are organized in a hierarchical manner, and we have vegetable products at the top. At the 2-digit layer, we have all the cereals, and at the 4-digit layer, we have rice, and at the 6-digit layer, we have different kinds of rice. This system is refreshed every 5 years, and it's something that we can rely on for doing our predictions going forward. Here are some examples with that intermediate HS code as a way to filter if a match exists or not. In the first two, we have a match in the HS code, and we provide the corresponding semantically matched EIF as the right EIF. In the third example, we have a car tire brush, and the closest EIF we have is a vacuum cleaner, which is another cleaning tool. That is the only relationship, but the HS codes are vastly different, and therefore here we can say that there is no appropriate EIF in the dataset. We performed this as an experiment for over 500 products, where every product is annotated by at least 3 people, and the majority vote, where 2 annotators agree, is taken as ground truth. When comparing against exact string matching or neural network based semantic match, our algorithm, Flamingo, outperforms them when we looked at the top ranked result. Flamingo includes that no match based on the intermediate HS layer, whereas we use thresholds in the case of string matching and neural matching. The human performance is still higher than Flamingo, especially when finding an appropriate match when one exists. And this can be an avenue of further improvement in future work. However, EIF selection is just one of many steps that we need to do in carbon footprinting. In our poster paper, also being presented at ACM Campus, we go through all the steps that are involved in doing an LCA, the challenges that are present, and different innovations that we can do to get across these bottlenecks and accelerate carbon footprinting at scale. All of our code and data set is open source, which you can find it at this QR code. Thank you.